In this lesson, we're going to be talking about paired sample t-tests. A paired sample t-test is a statistical procedure used to compare two means that come from the same sample. Now, in a paired sample t-test, each subject or entity is measured twice, resulting in pairs of observations. Now, these paired observations can represent things like measurements taken at two different times, like before and after an experiment. For example, company training programs where employee performance is measured before and after the program. Or measurements taken under two different conditions. For example, an experiment done in experimental conditions, then also done under controlled conditions, and more similar measurements. Now, when carrying out a paired sample t-test, the following assumptions must apply. Number one, that the samples are independent and are randomly selected from a population. That the difference between the paired values is normally distributed. And that there are no outliers in the difference between the two related groups. And by outliers, we talk of rare values that appear far away from the majority of the data. Now, for the paired sample t-test, the null hypothesis assumes that the true mean difference is equal to 0. That is, there is no difference between the two data sets. So if we have two data sets, the null hypothesis is such that mu1 is equal to mu2, which translates to mu1 minus mu2 being equal to 0. Now we can denote the difference mu1 minus mu2 as mu d. So we can say that the null hypothesis is that mu d is equal to 0. For the alternative hypothesis, it can be that mu d is less than 0 for a lower tail test, or mu d is greater than 0 for an upper tail test, or mu d is not equal to 0, and that's for a two-tail test. Now, after having stated the null and alternative hypothesis, you then, number one, calculate the sample mean for the differences. That's d bar, which can be found by sum of the differences over n. Number two, calculate the unbiased estimate for the population variance of the differences between the two groups. That's s squared d, which is 1 over n minus 1 of sum of d squared minus sum of d squared over n. Number three, you then calculate the test statistic, which is t, where t is equal to d bar minus mu d over s d over root n. But since from the null hypothesis we'd say that mu d is equal to 0, so the test statistic t will be d bar minus 0 over s d over root n. So finally, the test statistic t can now be compared to the critical value for the t distribution with n minus 1 degrees of freedom. So we're going to be working on this example as I demonstrate to you how we can perform this test. Okay, so let's work on it. The question says, employees at a particular company have been working 7 hours each day from 9 a.m. to 4 p.m. To try to reduce absence, the company decides to introduce flexi time and allow employees to work their 7 hours each day at any time between 7 a.m. and 9 p.m. For a random sample of 10 employees, the number of hours of absence in the year before and the year after the introduction of flexi time are given in the following table. So we have this data here in the table. So the question says, test at the 10% significance level whether the population mean number of hours of absence has decreased following the introduction of flexi-time, stating any assumption that you make. Okay, so let's work on this. Now, to start with, the assumption that we can make is that the population differences are normally distributed. So let's start with the assumption. So assumption, and we're saying is that the population mean differences or mean difference is normally distributed. So that's the assumption we have right here. All right, so we're going to state the null hypothesis. And for the null hypothesis is that the mean number of hours before flexi-time is equal to the mean number of hours after flexi-time. So that's the null hypothesis, which translates to mu b minus mu a being equal to 0. Then for the alternative hypothesis, since here we are testing to see whether the population mean number of hours of absence has decreased following the introduction of flexi-time, so we'll be saying here that the mean number of hours before is greater than the mean number of hours after, okay, which means that it has decreased from before to after. So we can write that as mu b minus mu a is greater than 0. So these two are the hypotheses. Okay, so next we shall need to find the differences d, which we find by subtracting the times before minus times after flexi-time. So let's have that. So that will be d. We'll take values. For a, that's 42 minus 34, which is 8. For b, that's 35 minus 32, which is 3. For c, that's 96 minus 100, so that's minus 4. For d, that's 74 minus 72, so that's 2. For e, that's 20 minus 31, which is minus 11. For f, we have 5 minus 2, that's 3. For g, that's 78 minus 61, so that's 17. For h, that's 45 minus 35, that's 10. For I, that's 146 minus 140, so that's 6. And lastly, for j, 0 minus 0 is 0. So these are the differences we have. Okay, so we shall need to calculate the mean of the differences. And for that, we shall first need to find the sum of the differences. Okay, so let's use the calculator for that. So here we're going to enter all the values. So I'll go to start mode, option 3, then 1. Then I'll enter all these differences. So we have 8, we have 3, we have minus 4, we have 2, minus 11, we have 3, we have 17, 10, 6, and 0. So we've entered all the differences. So now we can find the sum. So option 3, then option 2. For the sum is 34. So we have 34 here. We shall also need the sum of squares. And for the sum of squares here, that's sum and option 1. And we get 648. So we have 648 here. Okay, so we can now calculate the mean of the differences, which is sum of d over n, which in this particular case will be 34 over 10, which gives us 3.4. Okay, we shall also need the unbiased estimate for the population mean differences. So here that will be found by 1 over n minus 1 of the sum of d squared minus the sum of d squared over n. Okay, so we can find that. That's 1 over, since n is 10, we have 10 differences, so n minus 1 will be 9 of the sum of d squared, which is 648, and it's minus the sum of d, that's 34 squared, over n, which is 10. So we can do the calculation, so that will be 1 over 9, and that's off 648, and that's minus 34 squared over 10. And this is going to give us 59.15 recurring. So let's just have it as 59.16. So 59.16. Okay, so we can now calculate the test statistic, and we can find it by t is equal to d bar minus 0, and that's over SD over root n. Okay, so d bar, we have it as 3.4, and it's minus 0, and that's over SD, which is the square root of s squared d, and it's over root n. So I'll just write it as the square root of 59.16, and that's over n, which is 10. So this is how we're going to get the test statistic. Okay, so let's calculate that. So that's going to be 3.4 divided by, and here we've got the square root of 59.16, and that's over 10. And this is going to give us 1.397 going. So I'll just write it to 3SF as 1.40. So we have 1.40 here. So now that we have the test statistic, we can now find the critical t value. And since here n is 10, this is going to be to 10 minus 1 degrees of freedom, so that's 9. And since this is an upper tail test at 10% significance level, so the p-value will be represented by 90%, which is 0.90. So we're going to the tables for 9 degrees of freedom and 0.90, and we get a value of 1.383. So that's 1.383. Now for the test statistic we got here, you can notice that it is actually greater than 1.383, which is the critical value, which means that the test statistic lies in the rejection region, where there is evidence to reject the null hypothesis. And we know that rejecting the null hypothesis means accepting the alternative. So we can say that there is evidence to support the claim that the mean number of hours of absence has decreased following the introduction of flexi time. So that's the conclusion. So we can say that there is evidence that the mean number of hours have decreased following the introduction of flexi time. So that's the conclusion we can write here. And that's how we do it.